Hello everyone, this is Dr. Mo Shiva, Professor of Electrical Engineering Department at California State University, Fullerton. Purpose of this video is to do a review of Thevenin's and Norton's theorems. I have done two examples before. If you have not seen those videos, please go ahead and review those first. This is the third of the three examples. I'm assuming you're familiar with basics and requirements of applying Thevenin's theorem, and this is just a review example. Thevenin's theorem, basically, if you are interested in a load resistor or a network B in general connected there, we simplify a complex network into a practical voltage source, V Thevenin or V open circuit, and R Thevenin, look inside the box, or Norton's equivalent, which is a practical current source. Thevenin's and Norton's equivalents are related by source transformation, so VOC is RTH times ISC. Recommended methods are summarized in this table. In the first example, I did a video for the case where we have only independent sources and resistors. Second video, we had all three types of elements. And in this example, we want to look at the case where we only have resistors and dependent sources. Recommended method is to apply an external source. For this case, if we look at the Thevenin's equivalent, we're looking at a practical voltage source. However, since there are no independent sources in the circuit, open circuit voltage is zero, so that voltage source has a 0 volts, which means basically it's a short circuit. So Thevenin's equivalent will be just a resistor. To find the resistance, we do one of the two options. We can apply an external source. One is the easiest value to use. If we use an external voltage source, we look at the circuit and find current I, and then the resistance, equivalent of Thevenin's resistance, is 1 over I. Alternatively, we can apply a 1 amp current source, again 1 being the easiest number, find voltage V by analyzing the circuit, and then Thevenin's resistance will be V over 1. So let's do an example for this case. If there was a network B connected to this circuit or a load resistor, we assume it's already removed. We want to find Thevenin's equivalent of the circuit at XX terminals, so we apply an external source. 1 volt or 1 amp. For this case, a 1 amp is a little bit easier because the current through the dependent source there is known. So 1 amp coming to that node, according to Kirchhoff's current law, adds up to that current, and we get 1 plus 1.2 Vx. That's the current moving into the 10 ohm resistor. Current going down through 5 ohm resistor is voltage over 5. We're using passive sign conventions. So here we have Vx over 5. In other words, 0.2 Vx, same on the top, 0.2 Vx. Kirchhoff's current law, let's use it again. Current going down through the 3 ohm resistor is 1 plus 1.2 Vx, subtract from it 0.2 Vx, so we get 1 plus Vx. So all currents are known. We are looking for V, voltage drop from top to bottom across the 1 amp source. And V over 1 gives us Thevenin's resistance. Let's find V. Voltage drop is independent of the path. So start on the top X, move to the left. Through the 10 ohm resistor, we're talking about voltage drop. That being resistance times current, as long as we're moving in the direction of the current. So 1 plus 1.2 Vx multiplied by 10. Go straight down through the 3 ohm resistor. So we have 3 times 1 plus Vx. And bottom of the 3 ohm is connected to the X at the bottom, negative side of V. So we are done. This gives us, simplify, we get 13 plus 15x, 15Vx. So let's try to find Vx now. Let us apply Kirchhoff's voltage law to the mesh on the left-hand side of the circuit. Let's go clockwise. Starting at the lower left corner, voltage is negative. We see negative of Vx first, so negative Vx. Through 20 ohms resistor, we are moving against the direction of the current. Again, we are using voltage drop, passive sign convention. So current, if it enters positive terminal of the voltage, voltage is Ri. Against the direction of the current, you notice that going clockwise, we see the negative side first. So negative resistance times current, 20 times 0.2 Vx. Go straight through the 3 ohm resistor in the direction of the current, so 3 times 1 plus Vx equal to 0. Simplifying this, we have negative Vx minus 4Vx plus 3 plus 3Vx equal to 0. Negative 2Vx plus 3 equal to 0. So we have Vx. Vx is 1.5 volts. Let us find V. That is 13 plus 15 Vx plus 15 times 1.5, 22.5, and we end up with 35.5 volts. So this is the voltage generated across the 1 amp source. 1 amp results in 35.5 volts, which tells us Thevenin's resistance is resulting voltage divided by applied current, 35.5 ohms. That is Thevenin's equivalent of the circuit. So again, with resistors and dependent sources, the circuit is dead. Open circuit voltage is 0. So Thevenin's equivalent, same as Norton's equivalent, It is just a resistor. So that is the Thevenin's equivalent of our circuit. Look at my other videos regarding finding Thevenin's equivalent and future videos for using other methods for circuit analysis.